Hi, I'm Seven Yaakov. This presentation is entitled Gain Margin in PWM Converter. I'm showing here a generic model of a PWM converter. We have the power stage modulator, could be a voltage mode or current mode. Then we have the arrow amplifier around which we are going to have the phase compensation. And then I'm showing here also a divider that you need in case that the output is not supposed to be equal to the reference, higher than that. So this is the basic model of a PWM converter, which is a feedback system. Here is the reference, this is the phase compensator, and then we have the power stage modulator and the voltage divider. Now we know that the performance of a feedback system in closed loop really depends on the poles and zeros, and in particular, the system will be unstable if there are poles in the right half side of the complex plane. And we can test for it by the Nyquist criteria. Here it is, in which we have the imaginary part of the loop gain, and this is the real part. We have the unit circle, and this is actually the loop gain. Frequencies start from zero and go all the way to infinity, and then back to the negative frequencies. And we know that if the loop gain is penetrating the unit circuit below this 180-degree line, then the system will be stable because it's not encircling the -1 point, and the distance between this penetration and this 180-degree is the phase margin. And the phase margin can be seen in the Bode domain. And in this case, we see here the amplitude, and this is the phase. This line of 0 dB is actually the unit circle, and the penetration here is this crossover point. And if we look at the phase, the distance between the actual phase and 180 degree, 180, this is after taking into account the negative feedback, okay? So the distance here is the phase margin. And we know that the phase margin is affecting the dynamic behavior of the system. For a step, we're going to have an overshoot, which is a function of the phase margin. That is, the overshoot becomes larger and larger as the phase margin is becoming smaller. Same thing is for this peak in the frequency domain, where the peak is becoming larger and larger because the Q of the system is becoming larger, the quality factor, as the phase margin is becoming larger. So the phase margin is really a very powerful measure of the behavior of the system in closed loop, and actually tells how far is the system from oscillation. Gain margin is a bit different. And I'm showing now here again the phase margin and the gain margin for a system. This is the loop gain, and this is the phase. Now for the phase margin, we look for the cross of the 0 dB. Here it is, the phase here, and this distance is the phase margin. I've here added or subtracted 180 degree. So 0 is actually the 180 or 360 if you take into account the negative feedback. And the phase margin is therefore the difference here between 0 and any given point. So this is the phase margin. Now the gain margin is something else. We look first of all for the point of frequency at which the phase is already 180 degrees or 0 degree in this way of looking at it. And then we look at the gain of the system at this particular frequency. And then the difference between the 0 dB and this point is the gain margin. So in this particular case, we have a phase margin of 45 degrees. And the gain margin is this distance between, again, the gain of the system when the phase margin actually is 0 and the 0 dB. And in this particular case, it is 12 dB. So what it really means is the following. If I have a system and this is the gain margin and this is the 0 degrees, What it means is that if the gain of the system will increase and the whole line here, the loop gain, will be shifted upward due to this gain, then if it will be shifted by a gain of this distance, then the system will be unstable because then the phase margin is zero. So this actually tells us what is the distance from instability in terms of gain, not in terms of phase like in the phase margin, but in terms of gain. So we can say that there is a major difference between phase margin and gain margin. The main difference is that the phase margin determines the dynamic behavior of the system, as well as how far is the system phase-wise from instability. The gain margin is only a measure how far gain-wise is the system from instability. So to demonstrate this whole issue, I've set up an LT-SPICE schematics. There are two parts to it. And what it is a feedback system in which I'm actually describing the system by a Laplace expression, Laplace transform expression. This is the expression, and LT-SPICE is accepting it, so it can run it, and I can run here a time domain and a frequency domain analysis, that is AC and transient analysis. And in this particular case, I have three poles, one at a very low frequency, and then two poles at 1 kilohertz, in fact, same frequency, while here I have only two poles, and the AC analysis and the loop gain measurement is done by having here an AC source, so that during AC analysis it is activated. And again, if this is the signal going this way and then go all the way back here, then this will be the loop gain. Okay, so the ratio between this voltage and this voltage in the AC analysis is the loop gain. Very, very convenient to do that. So I have two systems with somewhat different loop gains, but I've made an effort such that the crossover frequency and the phase margin of the two systems will be the same. Okay, so I can compare them knowing that the phase margin is the same while the gain margin is not. So what we see here, that in one case the crossover frequency is 58 kilohertz, and the other one is a little bit higher, 67 kilohertz. However, the phase margin in the two cases is very close. This is 48 and this is 45 degrees. Okay, so we have two systems, different transfer function, but the crossover frequency is about the same and the phase margin is just about the same. And here it is in a zoom view. This is the crossover frequency. Here is the phase. Now the gain margin is then the distance between the 0 dB and the loop gain when the phase is already 180 degree, or in this presentation 0, because I've taken into account the negative feedback, so it's like 360 degrees. Now, as far as this system goes, you can't talk about the gain margin because the phase actually does not go beyond 180 degree. So the phase margin is really very large. You might say it's infinity. So I have here two systems with just about the same phase margin, very close crossover frequency, but a difference in the gain margin. Now the objective here is to see whether the gain margin makes any difference in the dynamics of the system given that the phase margin is the same. This is the objective of this simulation. And here it is. And we see that the response is just about the same. There's a small difference in frequency, and this is because the crossover frequencies are not exactly the same. Otherwise, the overshoot is just about the same, meaning that the dynamic of the system is just about the same, and therefore we can conclude that the gain margin does not make any difference in the dynamics of the system. It just tells you how far are you from instability in terms of gain? Now, the question is gain margin important in PWM converter? So I'm showing here what is like a synchronous buck converter. We have the half bridge here, the two transistors. We have the output section. This is the error amplifier, modulator, and there is a driver, of course, for these two transistors. And the system is fed by a power supply of Vin. Now, in this case, if we are looking at the small signal response, small d, the perturbation in the duty cycle, and its effect on the output, and I'm talking about the average, of course, signal, not the PWM, not the switching signals. Obviously, this response is a function of the input voltage, because this response is in fact the small signal duty cycle times Vin. Or let's just take an example. Suppose you have a 0.1 change in the duty cycle. The average voltage here will change like 0.1 times Vin. So if you change Vin, you'll get a larger signal, meaning that you actually increase the loop gain. So in this case, the gain of the loop gain is dependent on Vin. And we can model it by saying that there is another multiplier here by Vin. So we have a loop gain, and if Vin is changing, the magnitude of the gain is changing, and therefore the gain margin could make a difference. So to demonstrate this thing, I've set up you might call a hybrid average model to demonstrate this synchronous buck converter. In this case, I have this output section, L and C, and then I have the error amplifier. There's some phase compensation here. I'm generating a signal, which is the duty cycle. This is not a switching signal, but it's an average value of the duty cycle. And then I have here a multiplier of this average duty cycle times Vin, that is the input voltage. So we see here not the pulsating waveform, but rather the average values of these waveforms. Okay. Now, having this model, I can run, of course, an AC analysis and look at the loop gain, which is, of course, very convenient. So here it is. I'm showing here two cases for this particular model, one with the 5 volt input voltage and one with a 100 volt. So the 100 volt, of course, has a higher gain due to the reason that I've discussed. So this is now the 0 dB, and here is the phase margin of the system with 5 volt supply, and here is the phase margin of the system with a 100 volt supply. Obviously, we are moving this way, the gain is higher, and if the phase is going down, then the phase margin is, of course, becoming smaller. Here we have 62, and here we have 22. And if I look at it at the time domain, this is the 60-something degrees phase margin, and this is the 22. I'm not showing here oscillation because the gain has not risen enough to get into the actually oscillator domain, but we can clearly see here the effect of the reduction in the phase margin, making the overshoot much higher, and then oscillation, and this is something that we don't like, of course. So now let's have a look at a commercial unit, and this is LTC3703. It is a voltage mode architecture. That is what we are talking about, the voltage mode converter. So here is a test circuit of this unit, of this controller, and this is suggested by Analog Devices. What I did, I have added here an excitation, injecting current into this point. This is like a excitation, you might say, to the reference. We don't have access to the reference, so this is like having a change in the reference. I'm putting here a current source, so the impedance is not changing and the voltage divider is the same. Everything is the same except that I have here excitation, and I'm stepping now this source. This is the power supply of the unit, of the power section of the unit. and I'm stepping it between 15 and 100 volt. And here it is. This is where we have the injection of this excitation. And in this case, we see that in all cases, the output voltage we have exactly the same. So the response is exactly the same. There is no evidence of any effect of the gain margin. Well, there is a very good reason for that. This particular controller has a feed-forward arrangement. Here is a zoom of the relevant part. We have here the error amplifier. This is the output of the error amplifier. And here we have a divider. And the input here is the input voltage. This is the supply voltage. So there is a feed forward of the input, having here a divider. So looking at it now with this simplified model that I had earlier, we know that the input voltage or the supply voltage is actually multiplying the gain here. But now we have a divider which is sort of neutralizing this thing. So this particular unit has a built-in correction, and this is why it's not sensitive to the gain margin. Now what about current mode? Now current mode means that you have an inner loop of current feedback. Let's talk about peak current mode. Okay, we are sensing the inductor current, and there is a feedback loop here which is maintaining it, and it is compared to a reference which is in fact the output of the error amplifier of the voltage. Okay, so the inner loop is actually keeping the current to follow this value. In the case of the peak current mode, it's actually the peak of the current, that is the average plus the ripple, is following this voltage. So what we have here is actually we sort of eliminated the effect of the inductor per se and replaced it by a current source in case that the feedback is strong and that the bandwidth is sufficient. Then we have here a current source. If we have here a current source, then this system becomes to be a first order system. And this system is not dependent on the input voltage because we are, by the feedback, controlling the current, and therefore if there is a change in the input voltage, the feedback of the current control will sort of suppress it due to the feedback of this current. So let me just sort of reiterate here. If this is the current mode scheme, we have the clock setting up the flip-flop, turning on the transistor. The current of the transistor is going up, and when it reaches a certain value, this comparator actually will kick, and then there will be a reset, and the voltage of the gate will go down. Now, this process does not depend on the voltage here. That is, it's just looking at the current of the inductor. When it's getting to a certain value, it is changing the state of the gate drive. So therefore, current mode controlled PWM converter should not be sensitive to the gain margin. So now I'm going to test a current mode controller. It's very similar to the earlier controller that I've shown, except that in this case it is current mode, same family in fact, and this also goes to 100 volt. So they are very similar controller, except that one is voltage mode and this one is a current mode. And in this case, the current sensing is done by actually looking across this lower transistor, the voltage on it when it is on. Okay, so this is the sense, the plus and minus of the sense, and this sense now go into the comparator, which also get the output of the error amplifier of the voltage loop. So this follows the idea of peak current mode. And I'm testing this controller again by having current sources, in this case 2 current sources, which are injected into this point, which goes into the feedback point. It's exactly like I had it before. So this is actually like an excitation to the reference. And we are going to look at the output. In this case, I'm changing the power supply voltage between 15 and 100 volt. So let's first of all look at the 15 volt. Well, we see, by the way, that the response is much faster than the voltage mode, which is nice by itself. But we see here sort of an overshoot. Now, as it turns out, I think that this overshoot has nothing to do with the linear response. It is a matter of the slew rate limitation of the circuit. And since we have 15 volt and the output is 12 volt, the overhead here between 12 and 15 is sort of small. It's hard for the system to suppress the effect of the slew rate. Now, if I look now at the 65 volt and 100 volt power supply, you see that there is really no difference, and also there's no indication of any dynamic misbehavior, I should say, or being closer to oscillation or instability. So this system is really stable, except again for this glitch here, which I think is again due to problem of slew rate rather than the linear response. So what are the conclusions of this presentation? Gain margin is a measure of how far is the system from oscillation in terms of the gain. Gain margin does not affect the dynamic response of the system if the gain is not changed. We've seen that if a system has a very small or relatively small gain margin, it really doesn't make any difference as far as the response given a certain phase margin. Now, voltage mode PWM converter might be sensitive to the input voltage if they have a small gain margin. This I've shown. But modern PWM converters compensate for the gain margin problem by feed forward. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you have found it of interest and perhaps it will be useful to you in the future. Thank you very much.